In this video, we're going to look at tertiary structure. We're going to learn how we get tertiary structure. We're going to learn about what type of residues are found where in a protein, learn about what makes up tertiary structure, and see how this structure changes over time. Just a reminder over the levels of proteins. Primary structure is just your list of amino acids. Secondary structure are your alpha helixes and beta sheets, beta turns, local structure. Tertiary structure is one complete protein chain. So one N-terminus and one C-terminus folded into a 3D conformation. And quaternary structure is if you have multiple chains coming together to form a superstructure. Now first, let's talk about how we can determine the 3D structure of a protein, and one of the ways is through X-ray crystallography, or using X-rays to determine tertiary structure. And it's a rather simple idea, but there's a lot of hardcore physics and chemistry behind it, which we're not really going to go into, so we'll just stick to the simplified version. So first, the idea is that you take your protein, you get a very high concentration of it, and you try to turn these proteins into crystals. And it's actually super hard to do, and it's very much an art, just a lot of trial and errors. And there's not that much reason why crystal A will crystallize in one conditions and you get a crystal B in different conditions. Usually, you just purify your protein at high concentrations, use a bunch of different solvents and salts, and see if you can get a crystal. Now, if you get a crystal to grow, what you do is you take that crystal and you shoot it with X-rays while spinning the crystal 360 degrees. And this is usually done at a synchrotron. A synchrotron is one big piece of scientific equipment. Well, it's more like a scientific place where you have a giant magnet running around in a circle, and this is where you shoot a beam of electrons and they crash into each other, and physicists use this to learn about the nature of atoms. One of the things that comes off from a synchrotron is that when you're moving these electrons so fast, you actually get X-ray radiation, and we use that X-rays to look at crystal structures. And what you do when the X-ray hits the crystal, it will bounce, and we capture those bounces. What it's bouncing off is the atoms in the crystal. So you take this, your diffraction pattern, and you reverse engineer it to determine, okay, based on this deflection pattern, where were the atoms in my crystal? And that's what is electron density. So these spheres, these grids, are showing you where electrons are. And if you remember from basic chemistry, electrons are around atoms. So it tells you where your atoms and where your proteins are. Now, these crystals that we're making, about 40 to 60% of them will be water. And this is actually very important for protein stability because proteins are made in water. So if you didn't have water, they would unfold. The problem with this is that all that water leads to very poor X-rays. And you need good resolution or you won't get a good structure. It's almost like taking a photo. Like if I gave you a blurry photo and I asked you, what is this? You would not have an idea if it was incredibly blurry. Same with X-ray resolution. If the diffraction pattern is very, let's just say, blurry, then you can't see what proteins are in there. So for good resolution, your crystal must have your protein just repeating over and over and over again and in the same type of pattern. What this actually does is that it makes the X-rays are bounced off and makes those signals stronger and easier to capture. And making a crystal like this is incredibly easy from like a salt or just amino acids, but proteins are these big structures, so it's kind of hard to get them in this repeating pattern. And when we talk about resolution, you're going to see numbers in angstroms. A resolution for a protein under 3 is good. 1.5 angstroms is like the best you can do. It's very excellent. And to show you what that resolution means, here we're just trying to get a structure of this simple compound, this ring with 2 oxygens on it. It's 6 resolutions. If I told you, okay, place this ring, and I didn't have this red line here or these dots, you would have no idea how the ring was oriented. At 2 angstroms resolutions, you could start to put the ring, because these dark blue spots are telling you where the electrons are. So the only way to orient the ring is to have an oxygen here and an oxygen here. 1.5 resolution is pretty simple to do it. You only have one possible combination. And at 1.1 angstrom resolution, which is about nearly impossible for proteins, you can perfectly place your atoms with no difficulty. Now, since we're crystallizing a protein and shooting it with a laser and doing very complex calculations, how do we know the structure we get are reliable? Well, we have 3 pieces of evidence that says they are reliable. 1, they're still in solution, so we didn't take them out of solution, so they really shouldn't unfold. 2, if we ask different people to make different crystal structures of the same protein, we get the same structure back, which means that at least they're crystallizing the same, which probably means that's their native structure. 3, you can take a lot of enzymes that are in crystals and they will still perform their chemistry, which means that they must be in their active conformation. To show you some structures we've got from X-ray crystallography, here's HIV capsid, here's an antibody, ATP synthase, and the ribosome were all discovered using this method. Now, a separate technique that you've heard about in organic chemistry is NMR, nuclear magnetic resonance. And the idea behind NMR is that certain atoms, hydrogen, carbon, nitrogen, phosphorus, special isotopes, will actually absorb radio frequencies in a magnetic field. So the idea is you put your solution in a big magnet and you shoot it with radio waves and see what it absorbs. And the absorption, exactly where they absorb, depends on what they are around. Now we have 2 different types of NMR we can use. We can use what's called a COSY, and this will measure or tell us the distance between hydrogen atoms that are covalently connected through 1 or 2 other atoms. So think of the hydrogens on a methyl. We can tell where they are in space using COSY. While NOSY is interatomic distances for proteins, or rather the atoms of proteins are close in space. So we can see if 2 hydrogens are close in space, even if they're not connected. So using these distance criteria and chemical constraints we know from basic chemistry, such as bond angles, bond distances, group planarity, chirality, and van der Waals radius, you can make a picture that looks like this. What is being shown here is one protein with roughly 10 NMR spectra laid on top of it. And you can see that there's a lot of movement. The more movement there is, that's just saying that these atoms are really flexible. You get what's called an ensemble when you solve an NMR structure. The other technique we're going to talk about is actually rather new. It's called Cryoelectron microscopy, or Cryo-EM. And the idea here is you take your protein and you cool it to at 196C very quickly. And so quickly that the water actually doesn't have time to freeze, but it's just stopped in its tracks. If you remember, ice has a maximum of 4 hydrogen bonds. Water has on average 3.1 to 3.3 hydrogen bonds, so it doesn't have time to orient itself to that ice structure, but it's frozen water, if that makes sense. That's good, because if it was ice, it would completely destroy the protein. However, this hydrated protein remains in its native state. Then you can shoot your protein with electrons and you can start to look at the structure. And you can get really big, beautiful structures like apoferritin here through cryo-EM. Here is GrowEL, which we will talk about in a chapter from now or later on in this chapter. And this actually won the Nobel Prize in 2017 by these three gentlemen for the development of this technique for proteins. Now, when you look at proteins, there are different ways we can depict them. If you just show the backbone atoms, that's called backbone representation. If you show the surface, that's surface representation. These colors are kind of telling you, well, it depends how they color the protein, right? So it looks like these colors are saying what different domains are part of the protein. Another way to color with surface is charge. It's not being done here, but if you did, blue would be positive, red would be negative. Space fill is showing you your van der Waals radius. Cartoon is showing you your alpha helixes and beta sheets. Line is similar to backbone, but using just a different way to label things. Licorice is showing all the atoms but hydrogens. This is actually all 6 of these is the same protein, and you're going to see, if you continue on in biochemistry, proteins depicted in every way and more that I'm not showing. Alright, that's it for this video. I will see you in the next video.